And the next and last speaker for today's session is Sergei Popov, who is going to tell us about the surface magnetic field structure and whole evolution in the crust.
Okay, good evening. So I'm going to speak a little bit about magnetic field evolution, magnetic field decay. On Thursday, you'll hear two talks by Sophie Harp and Pires about diversity of neutron stars and their evolution, so I will not stop on it, but definitely you already heard that there are many different types of young neutron stars, and it would be nice to merge them in one evolutional picture. And such program, such framework is going on, and the main thing to explain this diversity and connections between different types of neutron stars is the magnetic field. So three main ingredients of such a unified model, which hopefully can explain everything. They are all related to the field. The first is, of course, the field decay. It does not only explain the evolution of magnetars, which are definitely living on magnetic field energy, but it also helps to explain, for example, X-ray dim isolated neutron stars, this Magnificent Seven, which are most probably remnants of magnetars. The next ingredient, which is important to explain things, is the opposite process, is the process of emerging magnetic field. Also already in previous talks we heard that after an episode of strong fallback, field can be covered by a layer of matter, and then it slowly diffuses out, and it helps to link, for example, central compact objects with the rest of population, I would say. And finally, the magnetic field topology is very important, and in particular, toroidal field is very important. As for the decay, there are many evidences. Typically, we hear about isolated neutron stars, magnetars, and well, especially magnetars. But just to give some extra illustrations, it is possible to probe the magnetic field evolution on a longer time scale, on a time scale of millions or maybe few tens of millions years, because we have high mass X-ray binaries, which are definitely not older, because massive companions simply don't survive for 100 million years, for example. And also the accretion rate is not high enough to really significantly influence the field evolution. And if you take spin parameters of a large population of high mass X-ray binaries, you can try, using modern models, derive the magnetic field distribution out of it and compare it with predictions of models designed for magnetars. And on the left figure, you see it. So we start with something shown with a dashed line, then magnetic field evolve, and it comes to the distribution shown with a solid line, so you don't have high magnetic field contribution, and the crosses shows what comes out from the data on high mass X-ray binaries. So there is nice correspondence. Indeed, in high mass X-ray binaries, we don't see candidates for highly magnetized neutron stars. Maybe just now there are some candidates which people think can be accreting magnetars, but in my opinion, it can be better explained in the other way. What about normal radio pulsars? Do we see field decay in normal radio pulsars? That's a very tricky thing. There are many different, typically population studies. In some, I would say most of them, people don't see any strong evidence for magnetic field decay in normal radio pulsars. In our opinion, typically it happens because people study the whole population for on a long time scale. And the answer is that normal radio pulsars, so neutron stars with fields like 10 to 12 Gauss, they don't experience significant magnetic field evolution on a very long time scale, a few million years and more. Andrei Goshev few years ago suggested a more, I would say, sophisticated way to probe it. And after we applied this approach to some set of pulsars with well-defined data, we found that in a very narrow range of ages, I would say several 100,000 years, we see strong evidence for moderate magnetic field decay. The field is normalized to the initial value, so the field decays slightly less than a factor of 2 in several thousand years. And yes. So the typical time scale corresponds to this value. And then, of course, we cannot continue this decay for a longer time scale, because then pulsars would disappear and the PP dot diagram would look significantly different from what we have. So we have to stop field decay somewhere here at the age about 1 million year at most. And that's an interesting thing, how to do it. It depends on the answer on the question what kind of decay we see. Either it is just a pure ohmic decay on phonons, which exist in the crust till it is hot enough, when the temperature is above a few tens of million Kelvin. Or the most important ingredient which drives the magnetic field evolution is the Hall cascade, which normally is working in magnetars, but of course it can exist also in less magnetized neutron stars. Simply the time scale would be longer. For the Hall cascade, there are several. I'm doing something wrong with it. Чем вот этим? Давайте снимем. There are several numerical models for the Hall cascade, and the interesting feature which appeared just a few years ago, at first in the paper by Gurguliatis coming in 2013, that after some time the field configuration comes to some stable configuration, and the Hall cascade is not important anymore, and this stage was called by these authors the Hall attractor. And this is quite an interesting prediction, and of course it's interesting to pinpoint it in some real population of neutron stars. And at first our idea was that probably we see that neutron stars appear at the stage of Hall attractor, and we can see it in normal radio pulsars. There are predictions about field configuration, but for radio pulsars it's not that important. I will show this slide once again later. It's important that there are independent studies of the magnetic field evolution, which confirms the idea of the Hall attractor. So that's another result by a different group of people. Do we see a Hall attractor in normal radio pulsars? We can play with parameters inside the neutron star. I don't have time to stop on it. We need thermal evolution because the field decay on phonons depends on the temperature, and we used cooling curves calculated by St. Petersburg group. And for parameters we are interested in, the Hall timescale, the Hall cascade timescale is comparable with the timescale for ohmic decay due to phonons. So this line is for phonons. This is age. This is the timescale. It increases because the neutron star is cooling down, and these lines are Hall timescales for different initial magnetic field. This is a very long timescale for ohmic decay on impurities. We can put all these ingredients, impurities, phonons, Hall cascade, and see what happens when we, at some age, we switch off phonons when the neutron star crust reaches some critical temperature, and then we can switch off the Hall cascade according to predictions of numerical models. So we can show it all together. Field is normalized to the initial value. Here, everything goes on and the field decays significantly, so it doesn't look realistic, it doesn't work. Here, there is no Hall cascade at all, and what happens is that phonons are not important anymore after the critical temperature is reached, and it looks like this is working. So the Hall cascade, if we believe in numerical models, is switched off in normal radio pulsars too late, at few million years, and the field already decays by a factor of 3 or 4, which doesn't fit our results. So unfortunately, we were not able to see the Hall attractor in normal radio pulsars. We can plot tracks on PP dot diagram, and to see the Hall cascade, the Hall attractor for normal radio pulsars, you have to be here, and there are very few pulsars observed here. But maybe there are other sources. And these lines, they correspond to field decay due to Hall cascade by a factor of so 2 E-folds and 3 E-folds. And these green symbols are the Magnificent Seven. And it looks like they might be close to the Hall cascade, according to the Hall attractor, sorry, according to numerical models, because the field decayed by nearly an order of magnitude, so they started here and then passed through the magnetar stage, maybe it came here. So they can be good candidates to look for the for objects on the Hall attractor. We can choose the best of them. Here is the magnetic field luminosity. It seems that stars which are closer to the Hall attractor might be more evolved, more relaxed, so they might have lower luminosity, definitely, because there is less field decay inside them, and probably lower field. So we have to look for objects here. Luckily, 1856 is here. It's the first and the best studied, maybe, neutron star among the Magnificent Seven, so we focus on it. Then I come back to this slide. There is a prediction for the Hall attractor from Gruglatas coming. The magnetic field on the stage of the Hall attractor should be formed of the dipole and the octopole of the opposite polarity. Here it's of the opposite polarity, plus some contribution from the next multiple L5. So here they are, how it looks like. Roberto Taverna calculated temperature maps for 3 cases. For dipole plus octopole, we call it model 1, dipole, octopole, and the small contribution L5, and as a reference model, of course, we use pure dipole. The main feature is obvious. The hot region is larger for neutron stars on the stage of the Hall attractor. And as we are going to see in next slides, it actually kills everything. So unfortunately, the model doesn't fit. So when we just fit spectral data, it's fine. We can also play with the effects of the surface. Everything is fine, but we come to the point which doesn't fit. We can calculate, we can fit the spectrum with a 2 blackbody model and look at the parameters. These 2D plots depends on these angles which were shown before, angle between the line of sight and the rotational axis, and the magnetic field axis, or the dipole axis and the rotational axis. And we see that normally for 2 models which corresponds to the Hall attractor, the hot part of the neutron star is larger, which contradicts to the observational data. And this is a very bad news for this idea. Pulse fraction is all right, temperature ratio is all right, but this wrong area ratio is a bad thing. This is the observational data to blackbody feed for 1856. And obviously we see that the hot part in this feed has smaller characteristic radius, and the cold part has larger characteristic radius. What we expect normally, there is some small hot area and a larger cool surface, but best fit models for model 1 and model 2 give the opposite result, and so unfortunately even in this case, we at least don't see any correspondence between the prediction of the model for the Hall attractor, for the model of the magnetic field topology, which is reflected in the temperature map, and the result of observation of the source, which seems to be close to that stage if it exists in nature. So to give you some positive result at the end, or at least puzzling byproduct, when we discuss different members of the Magnificent Seven set of neutron stars, we say a funny thing. So there are two well-known sources, 1856 and 0720, and for both of them, kinematic ages are estimated, and the kinematic age is larger for 0720. But 1856 looks like more relaxed. It has lower luminosity, it doesn't have any peculiar behavior, and probably it is a hint to the fact that magnetic field evolution can be different for different stars, for different initial magnetic fields. So normally when we model, we put the same law of magnetic field evolution for all initial fields. So parameters can be scaled, but we don't expect that evolutionary tracks on the PP dot diagrams cross. And here probably it looks like, if we believe in all data, in particular, we believe that kinematic ages are really representative for real ages of the stars. Then the evolutionary tracks must cross on the PP dot diagram. That would be an interesting thing. And of course, thing that makes our life less easy. Okay, here I come to my conclusions. Unfortunately, we were not able to find evidence for the Hall attractor looking at the population of radio pulsars, normal radio pulsars, or looking at particular sources among the Magnificent Seven. So probably if the attractor existed, it is reached later, and simply the sources we could study are not at this stage yet, or probably this stage doesn't exist. Then there is a problem. We have to stop the decay somehow, and it would be very nice to have such a stage. And that's it. So I just leave it with the references. Thank you.
Thanks, Sergey. There is time for questions and comments.
Just a general comment, not really about Sergey's talk, is if you want to take some parameter as a unifying factor, there is the possibility, as I've been saying, that there's angular momentum in fallback material, fallback disks, which can explain why AXPs and SGRs, as well as the extents, have same kinds of periods. And now that people start talk again about fallback material, just to have a reason why the field is first buried and grow, it is more likely that fallback material has angular momentum, and therefore it doesn't fall back spherically to bury the field. It's just there to store the angular momentum, and then we get back. One can explain a lot of things like these anomalous breaking indices, what looks like field decay, etc., just by allowing the fact that there's some fallback material with angular momentum.
Are there questions? Okay, if not, let's thank Sergey and all the speakers for this last session again.